The hidden physics of your microwave. Why it doesn't cook from the inside out. You are standing in your kitchen, staring at a cold, congealed slice of leftover pizza. You place it inside a nondescript metal box, press a few buttons, and listen to a low hum for 60 seconds. When the beep sounds, you open the door, and miraculously, the pizza is piping hot, perhaps even rubbery. It feels like magic. We use this appliance almost every single day. It has fundamentally changed how we eat, yet most people have absolutely zero understanding of what is actually happening inside that metal box. Welcome to the hidden science of the microwave oven. The biggest myth about microwave cooking is one you have probably heard your entire life, repeated by parents and friends alike. They say with total confidence that microwaves cook food from the inside out. They imagine some mysterious, penetrating beam that bypasses the crust of a potato, travels deep into the center, and starts heating it from the core outward. This is completely false. It is a misunderstanding of basic thermodynamics. A microwave oven cooks from the outside in, just like a regular oven, a grill, or a frying pan. But the crucial difference, the reason it feels so different, is the physical mechanism it uses to generate that heat. A regular oven uses convection, heating the air, which then heats the surface of the food, which then slowly conducts heat to the center. A microwave doesn't use hot air. It uses intense electromagnetic radiation to force the food to heat itself. To understand how we heat food without external heat, we need to look at the engine of the machine. If you were to strip away the outer casing and the control panel, you would find the heart of the beast hidden deep inside. It is a heavy, powerful vacuum tube called a cavity magnetron. This is not kitchen technology. This is high-grade military hardware. It was originally perfected during World War II for radar systems. Its purpose was to generate high-powered radio pulses to bounce off distant enemy aircraft in the dead of night. In your kitchen, its job is exactly the same, but instead of searching for planes, it is blasting your leftovers. It converts wall electricity into high-powered electromagnetic waves, specifically microwaves. These are on the same spectrum as light and radio, but they operate at a very specific frequency, 2.45 gigahertz. This means the wave oscillates, wiggles back and forth, 2.45 billion times every single second. Why 2.45 gigahertz? Why this specific frequency? The secret lies in the target of these waves, liquid water. Almost every food you want to heat contains significant amounts of water. A water molecule, H2O, is what physicists call a dipole. Structurally, it looks a bit like Mickey Mouse's head. The large oxygen atom is negatively charged, and the two smaller hydrogen ears are positively charged. Because of this separation of charge, the molecule has a north pole and a south pole, just like a tiny bar magnet, but for electricity instead of magnetism. Normally, in that cold slice of pizza, these water molecules are randomly arranged, just floating around lazily. But when you hit start, the magnetron fires up. It floods the metal cavity with that rapidly oscillating electromagnetic field. Because water molecules are charged magnets, they desperately try to align themselves with this field. Imagine the field is pointing up toward the ceiling of the microwave. Instantly, billions of water molecules snap to attention, pointing their positive hydrogen ends upward. But remember, this is a 2.45 gigahertz wave. Half a nanosecond later, the field flips and points down toward the floor. Instantly, those billions of molecules try to flip 180 degrees to face downward. Then the field flips up again. and down again. Up, down, up, down. These molecules are being forced to spin back and forth violently, 2.45 billion times per second. This process is called dipolar rotation or dielectric heating. Crucially, these water molecules are not spinning in an empty vacuum. They are packed tightly together inside the structure of your food. As they frantically spin, they are constantly crashing into surrounding molecules, fats, proteins, sugars, and other water molecules. This microscopic friction on a massive scale is what generates intense heat. So, the microwave oven doesn't actually make heat and push it into the food. It uses radiation to force the water inside your food to generate its own heat through intense atomic vibration. Now back to the inside-out myth. Microwaves at this frequency can penetrate food, but not indefinitely. They typically penetrate roughly an inch to an inch and a half, depending on how dense or watery the food is. They excite the water molecules in that outer inch-thick layer. That outer layer gets incredibly hot, incredibly fast. Then, plain old thermal conduction takes over to move that heat from the hot outer layer toward the cold center. If you put a giant frozen turkey in a microwave, the outside inch would be boiling while the center remained frozen solid. The heat has to travel inward. It does not start at the center. This mechanism leads to significant engineering challenges and odd phenomena. Have you ever noticed that the glass door has a mesh screen with tiny holes in it? That is a Faraday cage. Microwaves are relatively long, about 12 centimeters from peak to peak. They cannot fit through the tiny holes in the mesh. That screen keeps the radiation inside the box, so it cooks your food instead of cooking you. Inside that metal box, the waves are bouncing around wildly off the reflective walls. As they bounce, they interfere with each other. In some places, waves combine to create areas of intense energy called hot spots. In other places, they cancel each other out, creating cold spots where almost no heating happens. If you just set your food in a static position, one part would burn to a crisp while another part remained completely cold. This is why the turntable exists. The rotating plate is not a marketing gimmick. It is an essential engineering solution to move your food physically through the varied landscape of hot and cold spots to average out the heating process. This also explains the dramatic sparks you see if you mistakenly put metal inside. The thick metal walls of the oven are designed to reflect the waves safely. But a thin, sharp piece of metal, like aluminum foil, a twist tie, or the tines of a fork, acts like an antenna. The intense electromagnetic field pushes the free-floating electrons back and forth inside the metal. If the metal has a sharp point or a crinkle, the electrons build up rapidly at that tip. Eventually, the voltage difference between that tip and the nearest conductor becomes so high that the electricity rips through the air. That blue flash is plasma, air that has been electrified into a superheated conductive gas. So, how do you actually use this powerful, misunderstood technology effectively? It is not just a blunt instrument for reheating coffee. Here is the utility protocol for maximizing your microwave. First, the DO protocol. Deuse round containers whenever possible for heating. Electromagnetic fields naturally concentrate at sharp corners and edges. If you heat lasagna in a square plastic container, the four corners will absorb massive amounts of energy and dry out into hard crusts before the center is even lukewarm. Round or oval containers allow for a much more uniform distribution of energy, preventing superheated corners. Second, the don't protocol. Don't ever run the microwave when it is empty. This is crucial. The magnetron is designed to pump huge amounts of energy into the cavity. The engineering assumption is that there will be something there, food with water, to absorb that energy. If the box is empty, those high-power waves have nowhere to go. They bounce around wildly and eventually reflect back down the waveguide into the magnetron itself. This energy feedback can overheat and permanently destroy the expensive vacuum tube that powers the whole system. Third, the when protocol. When heating liquids like water or coffee, be extremely careful about superheating. This is a rare but dangerous phenomenon. If you heat water in a perfectly smooth mug, it can sometimes heat past the boiling point, 100 degrees Celsius, without actually bubbling. It needs a nucleation point, a scratch, or a speck of dust for bubbles to form. The moment you drop a spoon or a sugar cube into this superheated water, all the stored energy is released at once. The water can violently erupt out of the mug, causing severe burns on your face and hands. Always put a wooden stir stick in the water before heating, or let it sit for a minute before moving it to prevent this explosive boiling. In conclusion, the microwave oven is a marvel of applied physics sitting on your counter. It is a direct descendant of radar technology that helped win a global war. It harnesses the power of the electromagnetic spectrum to grab molecules by their electric poles and shake them until they get hot. It doesn't cook with mysterious inside-out beams. It cooks with friction rooted in the fundamental laws of physics. The next time you watch that plate spin around, remember that you are operating a high-energy particle accelerator to warm up your soup.